Hi everyone, this is the 6th video in my Formula Student series. The board has arrived, so let's get right into assembly, having a look at how to solder various different packages. So I've already got out all the components I'm going to be needing. Here they are. And a general rule of good practice is to start by soldering the smallest components, so in that case this will be the 0603 SMD caps and resistor. That's just because if you start with the biggest things, they'll get in the way of the smallest things, and especially something like these plastic dip sockets. You'll put them in, then try and get in to do a surface mount resistor or something, and you might end up melting the package and you get a smelly mess. Now, through-hole soldering is definitely easier, so I'd watch this whole video and then, if you're going to practice soldering, practice with through-hole first. So starting off with these small 0603 capacitors that are going to sit on the rear of the board, you can see the footprint is basically just two pads next to each other. You haven't got any nice holes, that's why they're not through-hole, they're surface mount. So what that usually means is you have to use tweezers or something similar to hold the component in place as you solder it, which I'll now demonstrate. So the first thing we need to do is actually free the capacitor from what's called the cut tape, which is how it's delivered, because they're too small to just have loose. So to do that, if you just get a nail in, you can usually separate the two layers of the cut tape like this, and then pulling back one of the layers you can then tip out some capacitors. And you've got to be careful not to lose them because they're very small. Next you want to get your tweezers. I'm a fan of these sort of bent nose ones, and place the component roughly where you want it to go. One thing that really helps with this is thin solder and a small iron tip. I've got the latter, but sadly the thinnest solder I have is still 0.7mm, which is quite large. Next you want to solder the pad that's on the side of your dominant hand. So I hold the soldering iron in my right hand, so I'm going to start with the right pad. Heat the pad up, add a very small amount of solder, and it will always look messy. The key part is remembering to clean it up, because a lot of people don't. So now you've got some solder down, you don't need to hold the solder anymore, so you've freed up your left hand to use the tweezers. Hopefully this works. I've rotated the board a bit. So grab the component long ways in your tweezers, then remelt the solder you just put on so that the component is held exactly how you want it. Orientation, nice and flat on the board, things like that. And don't worry if that solder looks messy. Then turn the board 180 and solder the opposite pad. And I'll go into more detail about actually how to solder for the through-hole parts, because they're, as I say, they're more basic. Now all that's left to do is clean up the mess that we made on the first pad. So if you rotate the board again, then the next thing to do is try and bring some of that solder off with your iron. The problem is, flux is what makes this easy, and now that the solder's been remelted once or twice, most of the flux is dried up. So if you don't mind making a bit of a mess that you have to clear up at the end, you can add your own extra flux. So for example, I have these flux pens, so what I can do is I can just dab that a bit with the flux pen, and that just helps the solder do what you want it to, basically. So if I run that now, you can see it sizzles a bit, but the solder just sticks to all the surfaces, and you don't end up with those little trails that follow the iron as you remove it. Hopefully that's in focus and you can see that bit of soldering we've just done. You can also help yourself by not starting off with 0603 for surface mount. Maybe something like 1206 would be a better starting point, to be honest. For me personally, 0603 is about the sweet spot for surface mount. And now I'm going to solder the rest of these caps. One thing I usually do, which I forgot to mention, is that first little bit of solder, I normally put that on before I actually place the component down. And then just as you place the component in, remelt that bit of solder, and that just makes it a bit easier. So for example, here I've got the second capacitor. I can grab it with my tweezers, remelt that solder I just put on, and there we go, the capacitor's already held in place. Apologies if it's not really in focus. For small surface mount parts like this, a steady hand is definitely a must, I'm afraid. But probably the most important step is once you've got the component held in with the solder on one pad, just make sure the component is exactly where you want it before you add solder to the second pad. Because once you've got solder on both legs, on both pads, the component's sort of fixed where it's going to be. And what you really don't want is a component that's not flat on the PCB, because that looks shit. So now that I've fixed all of my capacitors down, I'm going to go through each one, reflowing it and pushing them down with the end of my tweezers. This video probably won't be as helpful as some of the others because soldering really isn't something you can teach very well on video. So now that I've got them all lying nice and flat, I've just rotated my board 180 and now I'm going to add solder to the other sides. The main problem with thick solder is that it's very easy to add too much, which makes it a mess. Normally it looks quite nice if you use just the minimal amount of solder, which is a lot easier to do with thin solder. I usually put too much on. So now I'm just going back to the original side, cleaning it up a bit, just getting rid of those horrible sticky uppy bits, which usually are quite tricky to get rid of without adding any extra flux. So now I'm going to dab them all with my flux pen. And once you've added flux, all you need to do is melt it and then take the soldering iron away quickly before the flux dries out. Using flux like this does tend to make quite a mess. It leaves a lot of browny orange residue, so that's what you want to clean off with some kind of alcohol. But I wouldn't do that till you've soldered everything, because otherwise you'll clean it off and then immediately get loads back. Hopefully here you can see the capacitors I've just soldered, all looking fairly nice. The next surface mount thing is a 1K pull-up on the other side, so I can just flip the board over and that's going to go here. So it's just the same process. This time it's a resistor, but it's the same package. So the only significant difference is that resistors normally have some text on, at least at this kind of size. So that means you have to put it the right way up or it looks really bad. Whereas capacitors, you can put any way up normally. Hopefully you can see on this side the resistor's black and it's got some writing, some numbers on it. And then on the back side it's white. So you always want the black facing up, and if you're extra pedantic like me, you've got to make sure the text is also the right way up. So same process again, I'm going to push it away slightly. Add some solder onto the side of my soldering hand, not much. Then I'm going to turn the board so that you can see what I'm doing. Pick up the component, remelt the solder, push the component under. We just want it in to start with, and then we can take a break, let it cool down. Then we can grab it again, make sure it's perfectly aligned horizontally and vertically, and then I put the two ends of my tweezers together and push down on the component, and then I remelt it one more time, and that makes sure it's sitting nice and flat on the board. Now spin the board 180 and add solder to the other side, like that. Then dab it with the flux pen and reflow the solder on both sides. Hopefully you can somewhat make that out. Nice and flat, that's the important thing. And something else that's important is if you've got one of these brass wool things, they're very useful. So pretty much every time I solder, I then dump the soldering iron in there just to make sure that there's no crap on the iron, basically. Especially with surface mount, you can get flux that sits on the iron, then dries up and makes a sort of black blob, and the black blob can be the same size as the component you're trying to solder, which is never very good. One last surface mount thing to solder is this capacitor C11, which is a surface mount electrolytic package. So they're actually quite big for a surface mount. The main reason you'd use one of these isn't to save on volume, it's just to save on having to put a hole in your board, because that means you can have a component or some traces or something directly underneath this. Whereas if it was a through-hole electrolytic, you'd have pins going through, and that wipes out the back layer and any internal layers you might have. These are very much the same process, although they're a bit easier because they're bigger. So I'm going to start by adding solder to this big top pad. Then I'm going to try and grab this big capacitor with my tweezers. And while I melt the solder, push the capacitor into the solder. And I've got it in now, but it's very poorly aligned. This is big enough to use my fingers, so I'm actually going to push it around with my index finger until I get it perfectly lined up with the silk screen. Now I've reached the point where I've spent so long pushing it round, all the flux has dried out and there's not quite enough solder. So I'm going to add a bit more solder, which will bring with it some more flux. There we go, I don't think it's going to get much better than that. Like other electrolytic capacitors, surface mount electrolytics are polarised, but it's usually quite easy to get them the right way around, as long as you've used the symbol for a polarised capacitor in your schematic, because the footprints, I'll see if I can show you. Hopefully you can see here, but at the top of the footprint, the corners are sort of cut off, whereas at the bottom, it's a proper square. And it's the same with the actual package. It's basically got a big plastic base with the corners cut off. So as long as you line them up with the silk screen, you'll be good. Now I just need to do the same thing as before, which is add solder to the other side. I probably won't need to go back to the other side and clean it up with flux, because this is a lot bigger, so it doesn't have the problem that I've added too much solder. There we go, I'm pleased with that. Now time to move on to the through-hole stuff. So for through-hole, I'm going to start with the easiest part, which is the resistor. This is probably the first thing you should ever try and solder, because it's just so simple basically. 2 is the easiest number of pins to solder by far, especially when you've got nice long flexible leads like this. Resistors can go in either way around, although this whole board has a direction because it's got text on it, so it has a way up that it wants to be. And the order that you read colour codes like this one has gold, and gold should be on the right hand side because it's at the end. So personally, I'd always put resistors in that way around, but it doesn't actually make a difference to the circuit. What you want to do now is bend these legs as tight to the body as you can get, so you end up with something that looks a bit like this. Then push both of the legs through the holes, like this. Sorry, I've got very shallow depth of field on this lens, but hopefully you can see that they just pop through. And then what you want to do is, with one finger, push the resistor down so that it's flush with the board, and then with another finger bend the legs on the other side of the board out a bit to hold it in place. So on the top it should look like this, just sat where it should be. No gap there and not at a weird angle. And then on the back, the 2 legs should be bent apart like that. This is more important with some components than others, so resistors generally, because you've already bent the legs once, they've already got a bit of springiness that stops it falling through, but if you use an electrolytic capacitor like this, you won't have bent the legs, it'll just push through, and it can potentially, it might not completely fall out, but if it moves out a bit, it looks horrible. So now that the resistor's holding itself in place, we can just get our iron and get our solder, and we're going to start by pushing our iron into the gap between the board and the leg, so it should be heating both of them up. Then push the solder into the into all of them basically. Some people say don't let the solder touch your iron, but that just takes ages, and you might end up heating a component up too much. So I'll demonstrate it at a slightly more reasonable speed on this one. You can see I come in with the iron. Sometimes what helps is actually putting a tiny bit of solder on the iron first. That helps it heat up the other bits so you can move on quicker. So pop the iron in the gap, that should heat up both. Push the solder into, usually I push it into the iron to be honest. Then the iron melts it, but then the key thing is making sure it sticks to the other two bits. So you hold the iron there for quite a while, then take the iron off. And you want to end up with something like this, where the solder is clearly sticking to both the pad on the PCB and the leg that's being pushed through it. And there's no holes, there's no sort of weird gaps or anything like that. With through-hole you can usually get away with adding quite a lot more solder than you need. Although if you see a big ball of solder, then you've put too much. It should form a nice cone between the pad and the leg going through it. Then the final thing to do with through-hole components is snip off these leads. And don't forget to wear safety glasses or just shut your eyes. Now that's all of the, what you could call small components soldered. Next I'm going to do all of the sockets for the ICs, as they're a good step up to multi-pin packages. So I'll start off with this one in the corner. Just make sure all the pins are coming out of it straight, and then you should be able to just drop it in. The reason we use sockets is that it allows you to remove the chip, replace the chip if something goes wrong, and also it reduces thermal stress on the chip. So what you don't want is you don't want to damage the chip just from the heat of soldering it. There we go, it's dropped in. It's less critical with sockets, but still good practice to make sure there's a little notch taken out the top, just like your iPhone. And you want to line that up with the notch on the silk screen, because then when you come to put in the chip, you can line up the notch on the chip, and that makes sure that it's the right way around. Even surface mount parts have this kind of thing, but sometimes instead of a notch it might be a little circle or something else. There's always some kind of identifier. So like for example on the oscillator, this is a 4-pin package. You could quite easily put it all 4 ways round. So what they've done is they've made one of the corners pointy and the rest of them are round. And it's the same on the silk screen, so I just align the pointy corner with the silk screen. Now back to this tricky looking dip socket. What we're going to do is push it into the board with one finger just to stop it falling out and flip the board over. Then, and this is an important reason for doing smaller components first, we're going to try and quickly push the board down so that by pushing the board down we're pushing the socket up into the bottom. And don't worry about it being completely flat, we can sort that in a minute. What we're going to do is we're going to pick 2 opposite corners and solder those pins in. And basically those are just to stop it from falling out. Now that it's fixed in place, we can shake the board around and it's not going to come out. And now what I do, which I don't want to take any liability for anyone burning themselves, but this is what works best for me, is holding the board and then with one finger push the package up as you melt it on the other side. So basically that means when I reflow this pin I can push it up, and that just makes sure if I do that on both corners then the socket will definitely be sitting completely flush on the board. Otherwise if you just go straight in and solder all the pins, it might be sitting a bit wonky, and then you either don't care, in which case you're a bit weird, or you do care but you can't really fix it because there's so many pins to desolder. Then before you solder the rest of the pins, just take a look at how it sits on the board, make sure it's all good, it's the right way up and things. With just 2 pins soldered it's very much still possible to take it back out and swap it or do something like that. But once you've got all of them in, especially if it's a high pin count socket, you're kind of stuck. Now for the fun part, which is very easy. You just go through the pins one at a time, adding solder like we did for the resistor. It is definitely a skill that requires a bit of practice. It's not difficult to do, but to do it so it looks nice and you're very fast at it does take time. So don't get upset if it doesn't work perfectly first time. Something else that makes a big difference to how easy it is to solder is the type of solder you use. So I'm using dangerous lead solder. You can tell because it's on a red reel. But that does make it a lot easier to solder, because basically solder needs lead to work nicely, so the lead-free ones don't. But if you're watching this and you're on the Formula Student team, don't use this stuff at uni, because you'll get in lots of trouble. The next thing to do, which isn't always necessary on sockets, is just trim the leads, because there's still a bit of lead there and we want it to be fairly flush. You have to be careful if you're using high quality cuts like these not to go too far down, because these would quite happily chop off all the solder you've just put on, and then you'll probably have to get a new socket because the pin will be cut so short. So do watch out for that. What you can do is, if you want a method for that, you can lightly close them on the top of the lead and then push them down until they hit something and then chop, because then you'll be chopping all the excess lead, but they will have stopped as they hit the top of your solder. Now I'm just going to repeat that process for the other 10 sockets. There we go, all 11 sockets are now soldered in, and I think it looks quite nice. The next thing I want to do is the switch at the bottom that's going to be a button to press to reset the clock. That's one of these standard 4-pin DIP switches, and they're very nice because, I don't know if you can see, but the legs are a bit bent, and basically they're designed to snap in. So I push that in and now it just holds itself in. It would actually work without even needing to solder it, but of course I'm still going to. That just sits there. That just sits there like that, and then press it to reset it. So this is just like the rest, except it holds itself in, which is nice. So just go through each pin, adding solder really. These holes are bigger, the pads are bigger, and the pins are thicker, so it takes more solder than the bits we've done so far. It also takes more heat because there's more mass that you've got to heat up, so you have to hold it for longer. There we go. Now I'll just snip the leads. Switches usually don't have an incorrect way round, especially when they're not double throw. But normally, if they do have a different way round, you won't be able to put them in the wrong way round anyway. So this isn't actually quite a square, which stops you from putting it in at 90 degrees, which would not work. I'm going to save the displays till last to reduce the chance of them getting grubby as much as possible. And the next thing I'm going to do is, I think, the oscillator. So hopefully you can see on this symbol on the silk screen, as I mentioned before, you've got a pointy corner there and round corners on the others. So it should just be as simple as dropping this in so that the pointy corner's up there. Unfortunately, the text on the actual oscillator itself isn't going to be the right way up, which is a bit sad, but it isn't the right way up on this capacitor either. And the process for this is going to be the same as the sockets, so we want to sort of flip it round, and it's going to drop through a bit because the capacitor's taller, but as long as there's still some lead showing, we can add solder to the two opposite pins. Then we can push it up with our finger behind the board, and it might require multiple steps to get it completely seated, but you just want it so that when you melt it and push hard, it doesn't move at all. And you've got to keep holding it for a little while after you remove the iron. And then you can check as well, so you can see what I've done here is I've pushed a bit too hard on one side, so then it's lifted on the other side because there's some little blobs underneath it to lift it away from the PCB. So I want to make sure I'm pushing down on the middle of the oscillator, not on one side. There we go. I think that's done alright. Now I've just got to add solder to the other two pins, which is quite easy. Then I just need to cut my leads. Sometimes if you've got, let's say you've got a few really expensive components on your board, you might be better off not cutting the leads, because if there's a problem with the board or something goes wrong, it's better to still have the leads there so that you can reuse them for something else. So for example, if we look up here, this is a silicon carbide inverter, and each of these MOSFETs is worth about £20. So those, I haven't cut the leads on them, so that I can take them out and put them on a different board or something like that if I need to. There we go. Next up is the USB socket. So you can see, actually, if you remember from the video where we did the PCB design, I put JLC, whatever, on the silk screen so that they'd know where to put their order number. And I put that under the USB connector. And there it is. So they've replaced it with their order number, which they would normally just put anywhere, which wouldn't look very good. But now it's nice and hidden under my USB port. This is the same as all the other things. Flip it over, solder it, then reflow as you push it up. Most things are like that, to be honest, apart from things with long leads, like the resistor we did, or like a through-hole capacitor. Most things is just the process of getting it to not fall through the board. So this footprint actually it's got two mounting holes here, which are just connected to the shield, and then it's got the 4 actual data pins. That's because obviously when you're pushing in or pulling out your cable, there's quite a lot of mechanical force on it, so it has these extra big pins. So we're going to start by soldering both of those, and they're going to require a lot of solder. But for now I'm not going to add a lot of solder, I'm just going to add enough to tack it in so that I can push it up, because you can see, hopefully, it's not sitting flush with the board yet. So I need to push up and reflow my solder. There we go, now it's sitting really nicely. Now I can add the solder to my 4 data pins, and then I'll go back to the support pins and beef them up a lot. Because if you don't put enough solder on those, this connector might just get ripped out when you pull the USB cable. There we go. And hopefully you can see there's a lot of flux residue because I added so much solder onto this. And I'll show how to get rid of that shortly. All that's left to solder now is the 7-segment displays. So I'm just going to clean up a bit of flux residue here and here using an alcoholic wipe, and then I'll get to soldering those. So this is what I use to clean my boards. It's basically a wet wipe, but instead of whatever they put on a wet wipe, it's isopropyl alcohol, and they're designed for cleaning circuit boards. They also smell nice. This isn't required if you're just getting started. Don't worry, you don't need to buy special wipes or anything. This is just to make it look nice. Next, let's grab one of my digits. These are basically the same as the DIP sockets. They are still DIP, so they've got the 2 rows. So DIP stands for dual inline package. Dual because there's 2, inline because there's 2 lines, and then package because it's a package. I didn't realise these displays I've bought are actually made by Worth, that's what the WE is for Worth Electronic with a K because they're German. They make really nice stuff. So hopefully this will look quite good. So just pop it in there. Same thing as always. Flip the board over, don't let it fall through. Then add some solder. Now that I've tacked it in the 2 corners, we can have a look back and you can see that if I just added solder to all the pins, that's what it would look like, which is absolutely horrible. So now I can hold the board, push it with my finger, remelt that, and then go to the other side. You might want to do it a few times just until there's definitely no movement. A click like that's what you really want, so just as the solder melts, the whole display jumps forward and into place. If we flip that over now, we can check it from the sides, and that looks nice and flush now. So now I just need to flip it back over and do the rest of the pins, and then I'll repeat that process for the other 6 displays. So the next thing to do now is to put all our chips into the sockets. So I just need to make sure the right chips go in the right sockets. All of this row is 4026s, so I'm looking for the chips that say 4026 on them. And then I want to push them in so that the notch aligns with the notch on the socket. Once you've got one in, it's probably easier to just make sure the writing on them lines up. These chips can handle, I think, a supply of like 24 volts or something. They're very, very strong. But they're also very slow. That's the trade-off you've got to make. There we go, that's all the 4026s. Next is the other ICs, which is a bit harder to remember. I remember that the first one is the 4020 because I bought a special high-speed version of the 4020. And I'm going to use this little gadget that I have, because when you first buy a DIP chip, often the pins aren't parallel. So what I can do is I can drop this in here, give it a good squeeze, and now they're perfectly parallel, so it'll just drop into the socket. And as an example of the fact that faster chips are less tolerant of stuff, I think this chip's rated for like 10 megahertz or something, and it can only take up to 5 volts supply voltage. So now is an example of when you check the schematic. It's the only time we actually have to for this board, because all the components are so different. But these 3 chips that are going to go in these 3 sockets all have the same pin count, so we need to actually look on the schematic to see what needs to go where. Right, it looks like U5, which is the first one, is the clock divider. Then we've got the AND gate, and then we've got the inverter. So the inverter is this one, that's the 4069. I can just drop that in. I'm going to put all these through my little chip squisher. 4069 drops in there. Then the next one is the AND gate, which is the 74AC11. That's going to just go in here. And then finally is the 4024, which is the second binary counter. We've got quite a range of manufacturers on here. Just looking at the chips, we've got ST, all of these are ST, Texas Instruments, Motorola, I can never remember what this one is. I want to say Toshiba. And then the displays are all Worth as well. I can't remember. I think the USB connector's TE, because I always buy TE stuff. Rest of the components I'm not that sure. But here it is, the final thing. Right, so that's it for the assembly of the decimal clock project. I just plugged it in, and luckily it doesn't work, which is good, because that means I can do a follow-up video on troubleshooting and testing, which I think is probably the most important part of practical electronics. If something works first time, then you don't learn anything. But now for this video, I also have some other Formula Student circuit boards I need to assemble today. So I'm going to use those to demonstrate some other footprints, mostly surface mount, that I haven't been able to demonstrate here, such as SOT23 and SOIC packages. I'm even going to try QFN, which I've never done before and I'm quite scared of. So for our first bonus package, we're going to be looking at SOT223, which is this footprint here. In this case, it's for a little voltage regulator. And this process is very similar to the other surface mount components, although this is probably the easiest so far because it's nice and big. So I'm going to start with this pad. This is the heatsink pad and is usually connected to the middle pin, as it is in this case. So I'll just start by flooding that pad with solder. Then I want to try and grab my component so that it's the right way around, like that. And I'll rotate the board so that you can hopefully see nicely. I'm going to remelt this solder on the pad and push the regulator in. The problem that you might run into is that the regulator has quite a lot of thermal mass, which saps away some of the heat from your iron. But you just want to try and get it into a position where the other 3 pins are nicely centered on their pads, like that. And then just check it's flush with the board. If not, you can use the same technique as we did before, where once again we reflow it, but this time we're just using the tweezers to push it down. You don't want it to move anywhere except down. There we go. So hopefully you can see you've got the solder on the top big pad, which is what we just did, and then the lower 3 are now ready to accept some solder, which we're going to add now. And now that it's held in place, this is fairly trivial. just pop the iron so that it's touching both and add a bit of solder like that. Iron on both, add some solder, hold the iron for a bit, not too long, take it away. Generally, the bigger a component is, the easier it is to solder. Up to a point, then you need a beefy iron because they suck away all the heat. But that's our voltage regulator on. And the next things I'm going to do on this board are also relevant for this video. They're these little SOIC packages, which are basically like the evolution from DIP, just like the chips we did before on the display, on the clock. These are dual inline, but instead they're surface mount, and because they're surface mount, we can make them a lot smaller. So they just sit like that. Now I'm going to try and show you that these still have a little dot on them for orientation, but it's a dot in the corner instead of a notch taken out the top. Now I just need to check on this schematic which way around these need to go, and then I can show how to solder them. Right, nice, they go the correct way up. All I mean by that is that the dot's at the top, so which from your view is the bottom because I've got you upside down, and I can see it all fits nicely. Sometimes it's worth just checking you've actually got the right chip, the right footprint, things like that. So I'm going to start by adding a bit of solder to one corner. It's sort of like a combination of the dip sockets we were doing before and the just normal surface mount parts where you do one pin first. So now I'm going to try and pick my chip up and get it somewhere close to where I want it. I'm going to actually have to stretch my tweezers to be able to hold on to it. There we go. And now I'm going to remelt the solder that I just put on while I push the chip in, and hopefully that solder will mate onto that pin. There we go. It's a very bad connection though, but the main thing for now is that it's good sort of in the plane of the board. I don't know how to describe that kind of thing. So basically now the pins are all perfectly aligned to the pads. I just need to push it down. So again, push down with the tweezers, melt it, and now it's moved a bit, so I have to keep that melted and just really carefully push it around. There we go. That's where you need really steady hands. There's other techniques that work better for shaky folk, but I don't really know them, I'm afraid, because I don't need them yet. Give it a few years though and I probably will. Now just do the pin diagonal to that one to hold it in place, and then you can go through the rest. But right now there's very little solder holding it in place, so it could move quite easily. Now you can just run along all the pins, soldering them again. This is one where you do want a small tip because the pins are quite close together. But sometimes what you can do is put some solder on the iron and then just touch it to each pin, and each pin just takes the amount of solder that it needs off the iron. Now I can just turn it around and do the other side. And then this pin pitch isn't too fine, but especially on tighter pin pitches you just want to check every pin and make sure there's no bridges. So all I'm doing here is reflowing all the pins. Looks alright. Right, the next package that I want to demonstrate is SOT23, which is usually little transistors, but you can also get voltage referencers, voltage regulators, things like that. So here they are in a reel, just a 3-pin device. And I just did what often happens when trying to get one out, which is that it gets launched across the room. Luckily, it just landed here. So I'll tip a few out and I'll just demonstrate one or two of them. You'll probably start to see that despite differences in packages, the soldering technique is basically always the same, which is solder on one pad, put it where you want it, make sure it's flat, solder the rest of them. So I'm going to spin this round, and I'm going to start by putting solder on the middle pad, a bit like a tiny version of the SOT223 that we did earlier. Actually, I'll do Q1 because then you can probably see it a bit better. So there's a bit of solder on the first one. Now I've got to try and pick up the component. I've got to rotate it first. And now it's upside down. Some packages just love to always be upside down. Let me rotate this. Then just remelt the solder and drop it in where we want it. Wow, that went better than I expected. So that's now all nicely aligned. Now these pins take very little solder, so with solder as thick as mine, what I'll normally do is put a bit on the iron, and then before all the flux dries out, just quickly touch it against the pins. Like that. Sometimes it looks a little bit messy, but it's quite hard to do it so that it looks perfect on these little components. Hopefully you can see that both the bottom pins are soldered and the top pin has quite a lot on. Right, onto a different board. The next footprint we're going to look at is these little LEDs. It's a very common footprint called 50-50, which is because it's a 5mm square. These are particularly challenging because they don't have any pins, they've just got pads on the side. You can kind of see there. So I'm going to do the same thing as all the others, put a bit of solder on one of the pads, then I'm going to pick the LED up with my tweezers, remelt that solder and align the LED nicely, and then add solder to the remaining pins, starting with the one opposite. There we go, simple as that. That's all 6 pins soldered. Ignore this white residue, that just happens when you use solder with a lot of flux. Right, so now it's time for the tricky one, the QFN. So what is QFN? Well, you can see this is the footprint for it, and this is the package. It's got no pins, and it doesn't even have the sort of nice side ones. It's all on the bottom. So that looks like it's going to be fun. Now for this, you kind of have to use solder paste. So you can get solder paste in tubs or syringe. Dumb, drown yourself in your mother's. So you can get it in tubs or you can get it in syringes. This is a tub of solder paste, which is what I use. Syringes are probably more useful, but you can't put back in what you've squirted out, so you get more for your money with a tub. So just a quick disclaimer that I've never actually soldered QFN before, but I'm going to do what I usually do and pretend to be an expert on it anyway. Solder paste will also require hot air, so I'm going to turn on my hot air machine now. Hopefully it won't be too loud. And now I'm going to use this little spudger thing that I normally use to try and put a small amount of paste on that central square. This is what I've been advised to try. Just on that square, and then the rest of it we're going to see if we can do with the iron once the chip's in place. So there's a bit of solder, or solder paste. Solder paste is basically just loads of little balls of solder that melt and become solder once you heat them up. I'm going to try squishing all of that into the middle. This is probably a bit too much, so what I'm going to do is I'm going to sort of cut it in half and take half of it away. And I'm going to try and just make a little blob in the middle. And I just want to make sure, the most important thing is that I'm not shorting any of the pins, so we want the paste well away from any pins. Now I'm going to pick up my package with my tweezers. This is a little microcontroller in case you're wondering. And I'm going to place it on there. The silk screen helps a lot with trying to align it nicely. So you probably can't make it out on my 1080p camera, but you can just about see a tiny bit of pad on the sides, and you've got to try and line them up with the pads on the PCB, which is what I've done. Now I've got my hot air, so hopefully I can just blast this with hot air and it'll melt its way onto the board. Well, something's happening, I can see it all bubbling. What solder paste also does is it tends it tends to make components jump into the right place. So I just saw the whole thing shift a little bit. Hopefully you could see that on camera. And it's stopped bubbling now, so I'm going to remove the heat. And I can see quite a lot of solder's gone onto the pins as well, which is a sign I probably put on too much. Or it might have just been the perfect amount. The best way to test something like this is just to get your multimeter in continuity mode and just keep buzzing things out. If any two pins are connected that aren't meant to be, so like for example 2 ground pins would be internally connected probably anyway, but if 2 GPIO pins are connected then something ain't right. Luckily on this micro I'm actually not using very many pins, so it doesn't really matter if some of them are shorted, but you don't really want any shorted. Now with this I've got the problem that my probes can't actually fit in because the probes themselves will short out different pins. So instead of probing the pins, I'm going to probe where the pins go to. I guess the first thing to check would probably just be if the power rails are shorted. And they're not, so that's a good sign. I think maybe what I'll do is I'll just come in with my iron, add a bit of flux in to make sure the solder's in the right place, and then just build the rest of the board and see if it works. It's probably easier with this microcontroller to just see if you can communicate with it through the programmer. So, to be honest, what I'll do is I'll only populate the circuitry that's required for that. So that would be the voltage regulator, the header, some decoupling, but things like this has got addressable LEDs along here, they're quite expensive, so I won't put those in until we know the micro's working. And luckily this microcontroller only costs about £3, and I do have a spare as well. The bigger problem is that there's only about 10 available left, so hopefully they don't sell out if I need any more. Anyway, I think that's the final package I was going to show how to solder. So now that we've assembled our board, and I've also shown how to assemble more complicated packages on other boards, the next video is going to be looking at why doesn't the board work and how can we fix it. Thank you very much for watching, and until next time, goodbye. I'm going to show you now how much of a mess gets made when assembling boards.